Hello from the Forcetronics YouTube channel and welcome to Walking Around the Arduino Uno. So in this video we're going to talk about the supporting cast on the board of the Arduino Uno. So most of us know the ATmega 328P, that's the Arduino chip on the board. We know how to program it, we know that it has digital pins, we know that it has analog pins, we know it has pulse width modulation, we know it has different communication interfaces, but do we know a lot about the supporting cast, the other hardware on the board? And that's what we're going to talk about in this video and how it ties to the Arduino chip. So let's get started. Okay, so here we're looking at the Arduino schematic, the Arduino Uno schematic, the latest version, at least the latest version for the time of this video. One thing that might jump out at you right away is the fact that there's two big chips on this board. And in fact, the bigger chip is actually the smaller chip on the Uno board. So the ZU4 is actually the 328P, the Arduino chip. Over here, the U3 is actually the small chip by the USB connector, and this chip basically handles the USB communication, converts it to serial, and pipes it over to the Arduino chip so we can program our Arduino chip from the IDE. Now I'm going to dig into the different parts on the schematic, but let me first start with the power distribution system, and that's going to be at the top of the schematic. So let's zoom in there. Okay, here at the top we have the power distribution system of the Uno board. So this is going to route our 5 volts to our two chips. It's going to route our 3.3 volts. So let's start here, and this is actually the power supply connection. So you can connect an input DC. I think it's, what is it? Is it from 7 volts to about 12 volts? And that's going to come in here. And so what that's going to do is then feed in to the regulator, the NCP 1117. So this is going to take our voltage in and it's going to output a steady 5 volts. And if you notice these two capacitors, this 47 microfarad and this other 47 microfarad capacitor, these are actually these two big large metal cans on the board. And the reason for these large capacitors is they handle, I'll say, voltage transients and current transients and make sure that there's a steady V in and a steady output voltage to the Arduino. They serve as energy reservoirs, and that's why they're big. Also notice that we have V in here. So a lot of what they do on the schematic is common connections, they'll just label them so they don't have all these connections running all over the place. And you can notice that with ground. You can also notice it with the 5 volts here. But basically this connection point represents V in, and you could also see V in here. So we can get power from this input connector, or we can get it from the V in pin, and they both go through this regulator to give us a steady 5 volts. And then this 5 volts is fed throughout the board. Also here, once again, we see that 5 volts. This is going to give us our LED power. So this is going to tell us that once we get 5 volts here, it's going to tell us that the board is on, that the board has power. Let's go back over here to the left. Here's something that's not right away evident, but we have an op amp. We have the USB VCC, so this is from the USB connection, and this is the 5 volts from the USB connection. Then we have V in. So this is our V in, which is whether it's from the power supply connector or the V in pin. That's going to come in here, and it's going to feed through this op amp that's connected to a P-channel MOSFET. So what happens is if this MOSFET is positive, it's turned off. I should say if the gate here from this op amp is positive, it's off. So what that does is that feeds into this other LDO, which is the LP2985. And this is made by Texas Instruments. Here it is on the board. And this is going to take 5 volts in and it's going to convert it to our 3.3 volts. So a lot of times we'll use the 3.3 volts for a shield or for a sensor or for something like a Bluetooth module. So this is the regulator that's creating our 3.3 volts from 5 volts. Now back to this op amp. So what this is going to do is it's going to determine where is our power source. Is it from USB or is it from the V in or power supply chip? And if it's from V in, it's going to make sure the 5 volts comes from there, and that's going to power the 3.3 volt chip, or I should say the 3.3 volt regulator. If it's USB VCC, then this switch is going to be turned on so it acts like a short, and that's going to be used for that regulator. This op amp is not part of the power distribution network, but since it's up here, I'll talk about it. But this is basically tied to the SPI clock. So this connection is the same as this connection right here that's up here. So this is the clock for SPI, and all it does is it lights an LED when there's SPI communication happening. So this op amp, the LMV358, is actually a dual op amp package. So these two op amps are the same, and they both are on this chip, which you can see here on the board. So one is used for selecting the power source for the 3.3 volt regulator for generating our 3.3 volt supply, and the other one is used just to show when there's SPI communication happening. Okay, let's go down to the USB input as well as the USB to serial communication chip. Okay, here's the USB in. So this is where our communication from the USB is going to come that we have connected to our computer. Typically it's going to be coming from the IDE, the Arduino IDE. It's going to come in here. This chip, which is another ATmega chip, is going to convert it to serial and then use it to communicate or program the Arduino chip. So important thing to note, in case you didn't realize, that this is nothing but another chip similar to the Arduino chip, but it has its code on it. It has its design, its functionality already on it. It's running it and it's serving its purpose. So it's taking USB and converting it to serial. So walking around this chip, one of the big components here is the 16 megahertz oscillator. So you can see it here on the board, and that's going to basically serve as the clock signal for this chip. Okay, if we follow our, well, first I'll mention our transmit LED and receive LED. So when we have serial communication, we see these LEDs, they're flashing. That's coming from this chip. And then here is our serial communication lines, our transmit and receive. And if we follow them over, you can see they have some resistors in between. They're going to tie to the Arduino's serial connection, the D0 and D1 pins. So they tie in, they have some resistors here, and then you can also see that these pins from the Arduino, the 328P, are going to go to our header pins, 0 and 1 on our digital pins. So let's talk about the 328P now. Here it also has a clock source, a 16 megahertz clock source, and that's connected to the clock inputs, of course. One thing that's different though from the other chip we were just talking about is they both have 16 megahertz clocks, and I know in the Arduino's datasheet you can either use an oscillator, which is used over here, or you can use a resonator, which they're using over here. But that brings me to my question. One thing I don't understand is why didn't they just use the same clock or the same type of clock for each? Why did they use a resonator for one and a crystal oscillator for the other? I don't know. If anybody knows, feel free to comment. Here we can see the reset pin for the Arduino 328P, and if we go up a bit, here is the reset switch. So here is that push button switch. Here it is on the picture, that if we push it, it basically throws a reset into the chip. And you can see it's tied to some other functionality. It's tied to some pins. For instance, here's the pin we would tie to ground, this reset pin up here, if we wanted to put the Arduino in a constant reset state. Okay, here the Arduino chip also has the ICSP. So we can use pin 13 for the clock, pin 12 for the master in slave out, or pin 11 for the master out slave in, and also for the chip select, pin 10. But we also can use this header pin. So this just makes it easier for, I think it just makes it easier for shields to connect to that communication source, or for anything, I guess. So you have two options for SPI communication. You have this header pin, or you just have the normal pins here. But notice they're all tied to the same nodes. Okay, let's go down here. So we talked about VCC, and here's where VCC is fed into the Arduino chip to power the Arduino chip, and here's where ground is, labeled 7 and 8 on the schematic. Notice here though we have a ref, we have a VCC, and we have a ground. So this is used for the ADC. So you might be a little familiar with this if you watched my videos on increasing accuracy and resolution for your ADC measurements. But basically what this is doing is the ADC on the Arduino needs a reference. It needs a reference to use to compare its measurements to give you a value for the measurement. So the reference serves as the top value of the measurement. So for instance, we can see that AVCC, which is the reference input, is connected to 5 volts. So that means that our Arduino ADC can make a measurement from 0 to 5 volts. So this is serving as a reference. So if this 5 volts is not accurate, then our ADC measurements aren't going to be accurate. Now, with that said, there's also the option to input your own ADC reference, and that's what you do here at AREF. And if you notice, you see AREF here, but AREF is also tied up here. So it's going to be right above the ground pin and right above, or I should say right next to the ground pin, which is right after pin 13, digital pin 13. But that's what AREF does. So if you connect to AREF, you can, first of all, you can check the reference voltage that your ADC is using, and then I show in my video how you can use some simple register commands to actually change this and feed in a much more accurate voltage reference if you want. So that's what AREF is. AVCC is taking VCC and using it as the reference. For the ADC, if you want to change that, you just need to change some registers. So let's go over here to the, let's talk about the I2C communication. So we have serial communication, we talked about the SPI communication, and then finally we have the I2C. So I2C can be done in 2 places. So if we go to our analog outputs, or I should say our ADC inputs, we can see the SCL and the SDA pins. So these are the pins that are used for I2C communication, and they can also be used as ADC pins. So if you've used it before, you probably know that. In the newer version of Arduino Uno, they also have the pins up here. I'm not quite sure why they did it. I guess it gives you the option. Maybe it's easier for shields, or maybe it just gives you the option to have something on these pins and also connect to the communication signal, and you can easily switch. But this potential is the same as these potentials, so you can switch between the pins. Okay, and then lastly, let's look at interrupts. So if you're familiar, you may or may not be familiar with interrupts. I have another video on interrupts, but here are the interrupt pins, and they're going to be tied to digital pin 2 and 3. And so you can do up to 2 interrupts on the Arduino Uno. Okay, that's it for walking around the Arduino Uno. We looked at the schematic, we looked at the board, we looked at the supporting cast for the Arduino Uno. So I hope this gave you a better understanding of how things are working around the chip, not just the chip itself. And once again, the chip wouldn't work without the supporting cast. Some of the things I talked about, I have some supporting videos for interrupts. I talked about the ADC and how to get more accuracy. I also did some videos on sleep mode and the watchdog timer. So if you want to dig more into the Arduino chip itself, look around my channel, you'll find these videos. If you like what you saw, please subscribe to my channel. And if you have any questions, feel free to email me. Thank you for watching.